Hello, in this video we are going to learn about how to use simple regression and multiple regression and how to use inference based on regression. I know I said a lot of terms, so let me break it down into simple example. Let's say you are thinking of starting a new Starbucks outlet. You want to have a franchisee and you want to find out, hey, which location should I put my new Starbucks franchise outlet? Where should I buy it? And so as a human being, we are really good at judgment in terms of what are the factors that are important for a good location. Like we will say, hey, there's an income. The neighborhood where the location is should be very important. There should be less competition. And there are 10 or 20 such factors we can come up with that we can say, hey, these are important factors. So human beings are really good at that. But the problem is, if I were to ask you for that Starbucks location, which of these factors is the most important factor? That human beings are very bad at. If they go purely by their gut, and if they're not experienced, they are going to make a terrible mistake. And so that's where we use a regression. We use a regression which tells us for all the variables, what is the maximum weight I should give to which factor. So simple regression is when you have one factor, you want to find out like what is the prediction based on this one factor. Multiple regression is you're saying, hey, I have these 10 factors I want to take into account. The location, I want to take into account the income, I want to take into account the competition, and I have so many such variables, and I want you to then computer tell me what is the prediction. What do you predict will be my sales, or what do you predict will be my profitability? So that's all this board is. We're going to learn about how to use inference, how to build some sort of a prediction using linear regression. So let's understand first basically how to map out a linear regression. Then we'll go into a multiple regression. Then we will go into how do you build a prediction interval that tells you, hey, I'm going to expect this much sales. And then we're going to look at 3 important characteristics. These are the 3 error situations that we should avoid when we want to do errors in inference. So let's get straight into it. I'm going to erase some parts of this and I will recreate it. Okay, so the problem that we are going to embark is the following. We have a decision to make. What is the decision? What will be my profitability, or what will be my sales of my new Starbucks location, right? And then the one factor that we have to make this decision is like, hey, which income neighborhood, let's say. I'm only concerned about maximizing my profitability, the sales in my new location, by looking into income as a factor. And given an income of a neighborhood, I want to predict what will be my sales, right? Given an income of the neighborhood, I want to predict what will be my sales of my coffee shop, right? If I were to pick this location, which has this income in the neighborhood, versus that location, which has something else. So what do? The first thing you do is you try to collect data. And so what you do is you create like an Excel with 2 columns. First is income, and then the second one is sales, right? So you look at you try to find data that exists today. You look at existing outlets and you see what neighborhood. So let's say this is the neighborhood income of greater than $50,000, let's say. And then this is a neighborhood A. And then there's income neighborhood with greater than $80,000. Let's say this is monthly, right? And so you try to find out all the neighborhoods and you try to classify them in terms of like, hey, what is their income segment of that neighborhood? And then what do? You look at and try to sample like how much sales those existing neighborhood outlets are making. So you can find out, hey, this neighborhood income, they're making $100,000 in sale. But when the income goes up, oh, they're making $120,000 a sale. So on and so forth. So you collect data. That is the phase one. You collect data between the two variables. Data collection. You want to look at existing data as to, hey, what is the income category of this neighborhood and what is the sales in existing stores? There's lots of services that you can use to predict this, but you can even do simple sample. You can even like just stay at a neighborhood and then look how many people are coming by, what is the traffic volume. You can even predict like what is their sales and things like that. So there's various ways for you to approximate this. Once you collect the data, then power starts to happen, right? The power of the computing starts to get behind you. So what happens is you can in Excel very quickly plot a regression model by going to Excel data pack and then enable the data pack, and then you can have a regression model. So it will take in these two columns, column A with a neighborhood and then income or sales, and then it will give you a plot, a line plot, and it will also look at all of these data points, and then it will give you this plot. Basically, it's saying for this income neighborhood, this was the sales, so this is sales. So the way, and then there are many such points, right? Each of these points are basically these rows. So each of these rows are converted into a point. On this x-axis is income, y-axis is sales. And so what you do is you build this linear regression model, which basically looks at all of this data, and then it tells you what is a prediction line. It will build this line. This line is the linear regression line. This is what we call the linear regression. In a sense, all this is it's trying to minimize the distance of the squared between each of these data points and this line. So first it will draw this line and say, hey, the distance is like, let's say 100 from each of these points. And then it will draw this line and it will keep drawing. It's the power of the computer. So the power gets behind you because then the computer can draw each of these lines and find out, hey, the distance of this line, this golden line, from all of these data points is the minimum squared sum of distance. Sum of least squared, that is simple regression. It basically says the sum of least squared distance from every possible line. And then what it does, it gives you a prediction line. That is where gold is, right? That's the gold. You now have a prediction line. A line that basically tells you, hey, given any income, I will be able to tell you what the sales is. Isn't this powerful? Once you have a prediction line for a given input range, you can predict like what will be my sales. Now this is just one variable. We looked at income, right? What if I add another variable that says, hey, competition. I want to look at competition and sales. So you can have another column here, competition. Look at the competition in that neighborhood and then point out. And then you can keep doing this for every variable. When you keep adding new and new variables, this is variable 1, variable 2, you can still use regression. It's called multiple regression. And the way we denote this 1 variable regression and 2 variable regression is by this formula. SRM is a simple regression model. It's basically saying y equals to beta 0 plus beta 1 x1 plus sigma or some error, right? Which is nothing but an equation of a line. This is an equation of the line. This is a constant. This is the slope. This is the x1, which is the variable. And this is some error, right? Which is, there's going to be some error in this regression. But when you have an MRM with more than one variable, you see beta 0, same as SRM, beta 1 x1, beta 2 x2. See, we have a new variable now. So it can look at each of these variables and then give you a combined, so let's say this line was going this high and this line was going this way, then it will give you a combined line which will be somewhere in between, right? It will not be this, not be that, it will give you this line, right? So this is basically, it will be able to combine in a 3D space. Imagine this has like both the income and the competition in an MRM. MRM is nothing but taking more variables and plotting it. And then the equation, again, this is an equation of a line in a 3D space. 3D space, okay? So MRM is nothing but you're now drawing this line which says, hey, given all of these variables, I'm going to go and try to predict that this is how, giving me any variable, I will tell you what is the sales. So we looked at SRM, which is nothing but a prediction. Given a variable, what is the prediction? MRM, given multiple variables, what is the prediction? And the beauty of all of this is super expensive to compute, but Excel can do this. And there are many advanced software that can do this even faster and better. But we can do this with Excel. We can get really complex modeling done in Excel, right? And so this is the decision. Now the question is, can I rely on this prediction line to make a decision? That's where you're saying, hey, can I use this to make a prediction? And so for that, there are 3 rules that we need to check before we make use of this line for making a prediction. Making a prediction is nothing but inference. You're saying, hey, you build this regression model. Can I use it to make a prediction? 3 rules. So let's get into those 3 rules. So we understood what a simple regression is, a multiple regression is. And error, again, I want to just close on this. Error is nothing but, it's a normally distributed from 0 as the mean and sigma square is the variance. So errors generally also have, due to central limit theorem, errors also have a normal distribution. So that's a little bit of detail, but in a sense, all we need to understand is that SRM and MRM are basically prediction model. And now we're checking, can I use this to predict? So what are the 3 conditions? There are 3 rules that we need to check before we can get to using these models to make a decision. So the 3 conditions that are important before we can use our regression model that we build in Excel to check whether we can use it for inference or prediction. The number 1 is that the errors should be independent. So what does that mean? So let's say this is our y-axis and this is our x-axis. I'm drawing this purposefully at a slant, and I'll explain why. And let's say this is parallel to x-axis, right? So if our errors are independent, our distributions would look like this. But if our errors are not independent, our distributions or our sampling, our predictions would be above and below, right? It will be concentrated above and below, right? So when that happens, you cannot say that the errors are independent. Errors are clustered, sometimes below, sometimes above. They're not, it's not a cloud of errors above and below, right? So in this case, a simple way to check is if you draw a residual plot, and then if you see errors like without clustering, right? Then you can say, hey, this is independent errors. Look at this one. We see errors here with residuals below and residuals above. So when residuals are above and below your prediction line, if this is your linear regression, but if you see residuals above and below, then that is the violation of independence. Meaning the errors are concentrated above and sometimes below, but they are not like normally distributed above and below at the same time. So that is the first violation. The first violation is that the errors, if they are not independent, then that's a problem. You cannot use inference on this statistical model. What's the second problem? The second problem that we need to check is that the errors need to be normally distributed. So if this is our graph, then our errors should be normally distributed above and below. But if we see a graph that looks like this, and this is not normal distribution. A normal distribution typically is the bell curve, right? So our errors need to be normally distributed. So if you look at this, right, when you draw the histogram, the errors are not normally distributed. And so this one if this is how your prediction, linear regression prediction looks like, or an MRM looks like, then they are not normally distributed. So that's a problem. So it needs to have a normal distribution for you to use inference. So that is problem number 2 that you need to check. What is problem number 3? Problem number 3 is that the errors should have equal variance. So what is that problem? How do we plot it and how do we see it in action? So this is our x-axis, and this is where our model is used to check for errors that have the same variance. So let's say first time your model for a given location predicts that this is how it predicts, and then it predicts much wider, and then it predicts even wider, right? So if you see the width is expanding, and when you see the width expanding, right here it's like this high, the errors are not concentrated and not like equal above and below, then this is violating that the errors have the same variation, right? This is not having the same variation. The variation is basically above and below. What is the width? Is that the same? Ideally, you should see errors that are like this, right? It should be you should see it as a tunnel. The width shouldn't be increasing, or the width shouldn't be like decreasing, right? So that's the high variation error number 3. So if we check for these 3 errors, there's no clustering of outputs above and below. There is no there is a normal distribution, and there is no like abnormal, like not a bell curve distribution, and that the errors have variation that is of the same width. Then if these 3 conditions are satisfied, there are many more conditions, but these 3 are basic. Like there's temporal conditions, spatial dependence, and a whole host of other conditions. But let's say these 3 basic conditions are satisfied, then we can use our linear regression model or our multiple regression model for inference, which is to say prediction. So these 3 are important characteristics. Errors need to be independent, errors need to have a normal distribution, errors need to have equal variance, and that's how these 3 plots are. The final sanity check. If you, let's say, have a linear regression that looks at income from, let's say, 100,000 to 200,000, that's your data points. These are the neighborhoods you've looked at. And then you built this fantastic linear regression model that tells you, hey, what are my sales? And now if you use this to predict for 500,000, like you're trying to use it for data points that you don't even have samples for, then that's called extrapolation. Extrapolation is a mistake where you try to predict for data that you don't have any insights about, right? So that is a problem. You might say, hey, isn't that why we need a prediction? But you need to have the interval. You need to only predict within an interval. If you get a new data point that has never been looked at, then using an old set of data points to regress against and to predict with is stretching it too much. So that's the final tip in terms of how we can use our linear regression models, checking for these 3 conditions that are errors, right, for our prediction. Follow these 3 conditions, then we are in a good shape. So we've looked through SRM, right, where we saw income and sales. And then we looked through MRM, where we saw, hey, income has a positive impact on sales, but then there's this other variable, competition, which has a negative impact on sales. So you can start to draw these diagrams. How do you draw these diagrams? Well, Excel does this for you. When you run a regression in Excel, the sample output looks like this. It says summary output, and then it gives you a bunch of statistics, and then it tells you for each of your variables what is your coefficient. So in this case, let's say income. I'm going to take income, I'm going to say competition, right? And then it'll give you all of those variables, and it'll tell you whether this is a positive or a negative correlation and how big. This could say, hey, this is the 0.1, and this is like 7.5, 6.0, and things like that. So Excel will give you each of these statistics as output. So this coefficient here is basically telling you what is the positive or the negative relationship of income. It says 0.1 plus, meaning it has a positive correlation. And then it'll also give you this thing called standard error, which basically, remember our errors, right? So for every variable, there is errors. So the errors, it will tell you how is this varying. You can say, hey, this varies plus and minus 0.3, this is plus and minus 0.01, and it'll give you all of that. And then it'll give you this t-stat and p-value. T-stat is coefficient divided by standard error. So anything absolute greater than t-stat greater than 2 is huge, meaning it's significant, or p-value less than 0.5 is significant. So Excel gives you all of this data. It will also give you data around R-squared, which is basically saying, for each of these variables, what is my coverage? What fraction of my data points I'm able to explain with this? Higher the R-squared, the better. Adjusted R-squared will be a good proxy to look at, especially if it's not an SRM, where it will give you, hey, which of these weights, which of these variables are actually contributing to the prediction. So this will, adjusted R-squared almost always is less than or equal to R-squared. And so adjusted R-squared is good to look at in terms of coverage, like, hey, how much of my data is explained by this model, this regression model. And then there's this F statistic, which is an important one to look at, which basically tells you that, hey, each of these variables really don't have any prediction power. So that's the null hypothesis. And F statistic, if it's high, that's great. And if its p-value is significant, that's all we need to look at. High as in double-digit high, and p-value is less than 0.05. That means this whole model is not a throwaway. So look at the p-value of the F statistic. That'll tell you, hey, can I really rely on this model? So all of this data we get from Excel. So once we get those positive and negative coefficients, we can actually build, using the data, what are the variables and what are the impact, right? So let's say income has a +7 impact on my sales, but the competition has like a -20, right? And then I find out, hey, there's this positive correlation. Those places where there's high income neighborhoods, the competition is high. And so you can see that there's this negative loop happening here. Similarly, we can add another variable that says, hey, are there school district nearby, right? Is there schools nearby? And then the schools could have a positive or a negative effect based on the regression. And you can start to build your model that you can quickly realize what is it that's really impacting this. And very quickly, using adjusted R-squared, you can say, hey, this is, I considered this variable, but it's not that important. I can actually simplify it with these 3 variables and things like that. So the key takeaway is human judgment is good at factors, like what are the factors, but then you should use Excel, you should use the power of computer behind you to tell you what is the weights, how important is income compared to competition, right? And so when you have all of these weights, right, these are called partial slopes. Partial slopes as in, because they are all combining. The reality is that this model is a simplification. There could be 50 things, 100 things, 1,000 things, right, that really impact your sales. It could be how good is your manager. It could be what time do you open. It could be what is the crime rate in your neighborhood. There's hundreds of things. But what we're trying to do is we're trying to use our judgment to get to an adjusted R-squared that's high, that is statistically significant, and we're trying to use those variables that actually have an impact. So first getting all of those variables and slowly removing those variables will give us a model that'll be a good prediction. And then we have to check for those 3 conditions. Remember? So once we have, these are all partial slopes, right? But if we only have one variable, let's say I'm just going to say income and dollars, then this is marginal slope, because it's assuming all of those hidden things actually happening. So this is a marginal slope. So this slope encompasses actually all of the factors, right? But it can only do certain factors that it can proxy. So that's where you can see that, hey, the coverage might be low. So that's an indication that, hey, we need to increase our number of variables. We need to get better at reducing our errors, right? Because what happens is the next step we do with this after the error condition is checked is we want to predict, right? If this is our variable, this is our regression, we want to predict, hey, what is my prediction interval? Which is basically saying, you're saying this is my regression line. If I were to give you this data point, what is your prediction interval, right? So prediction interval is y hat plus or minus 2 times standard error. So y hat, you can find the equation of y hat from here, right? Y hat equals beta 0 plus beta 1 x1 plus standard error. And we can get this from the Excel regression statistic summary table, and we can also get these two. So we can get y hat for a given value of x1. So let's say we are given to predict for this neighborhood, we can get y hat. Then we need to add standard error. So Excel also gives you for, in the summary statistics, standard error for the entire model. So you add those standard error and you can predict with high confidence, once you have checked the error margins, hey, what is for a given value of x, my prediction is plus or minus 2 times standard error above and below. So this is basically 95% confidence. The detail here is that you get 2 from a Z statistic confidence interval of 95, or alpha equals 5, right? But basically you get y hat and then you get standard errors from your regression model. Then you do plus or minus 2 times standard error of regression model, you get this interval, which tells you, hey, I'm 95% confident. Look at this magic. It tells you that for this x, I'm 95% confident that your sales is going to be between these two ranges. Isn't that powerful? But let's say if you want to get 99%, then all you need to do is increase your standard error, right? So you go to 2 to 2.3, right? Because that's the 99% set statistic. But look at the power here. We understood how the computer can tell us what is the range. This is very powerful, right? We understood the 3 types of error. We understood R-squared. We understood how to use this data to make decisions. This can be used to so many examples. What example would you use it? The one example that came to my mind is I wanted to predict what is the number of hours that I would sleep on a given day, given certain variables, like what time do I go to bed, how much do I eat, when did I eat my dinner, was I stressed the day before, right? If you want to, or the temperature, right? Is it cold? Then I'm going to sleep more. So I wanted to use that for that. Another example that comes to my mind is like I wanted to predict the cholesterol levels in my blood based on various factors, right? There could be weight, there could be water, there could be so many factors that can predict whether you are high cholesterol or not. So there's just so much data around that we can use Excel. We can use Excel using simple linear regression. We can enhance our models. I want to know from you in comments, what are you planning to use Excel regression to tell you what are you trying to predict? What are you trying to predict? I want to hear from you in the comment section below. Tell me, what is it that you are excited about using this to predict? Thank you.